Hello, I'm Nicholas Solomey, and this is my NIAC Phase 3 project. It is a CubeSat space test flight of a neutrino detector capable of operating in space. This project started off as a NIAC Phase 1, mostly a simulation study, and then went on to a lab detector R&D NIAC Phase 2. And the current NIAC Phase 3 is the idea to construct a 3U CubeSat that we put into polar low Earth orbit to study the backgrounds that this detector would see in deep space and confirm its operation in abilities in space. And the goal is to hopefully have it launched by the fall of 2024. Eventually, a mission going close to the sun called the Neutrino Solar Orbiting Laboratory is hoped for. And that was under a NIAC Phase 2 development and budgeting of what it really would cost. This project is, of course, a cooperation among many different institutes. Here at Wichita State University, both the physics, the aerospace engineering, and electrical engineering is involved in helping on it. NASA's Marshall Space Flight Center in Huntsville, Alabama, the South Dakota State University, the Jet Propulsion Lab, as well as University of Minnesota. The R&D effort started off after the idea was conceived of in 2015 with a NASA EPSCoR partnership development grant, eventually led to a few smaller grants, including a NASA summer fellowship, where we developed the idea for this proposal. We submitted it and we received a NIAC Phase 1 in 2018, a NIAC Phase 2 in 2019. We had a small 3-month grant from Marshall Space Flight Center, CAN cooperation, as well as now we're just starting in October 1st of 2021, the NIAC Phase 3. And so this project so far has had about $2.8 million of studies, funding, and we're working to secure a launch assignment in 2 years of operations. We've already secured a space communication and networks near Earth networking communication grant. The detector component in green here is a GAG crystal, which is made up of 20% gallium. It has a large and fast light yield, such that when a solar neutrino comes in, it can produce a conversion electron depicted here in red. The gallium then goes to an excited state of germanium, which then decays to a well-known gamma ray with 2 different half-lives, depending upon which mode the transition occurred to. If we could operate a neutrino detector in space, what new science could be done? Well, just by going close to the sun, where Solar Probe Plus goes, we hope we would be able to achieve 1,000 times the neutrino flux that we have here on Earth. And we would hope that we would be able to detect a lot more solar neutrinos, as well as study them at closer distance to the sun, where the position resolution of the detector would be much more beneficial than, say, here at Earth. A 1 kilogram detector, of course, would be equal to 1,000 kilograms if you're operating it there at 7 solar radii, where the Solar Probe Plus currently is able to go. And if we eventually achieve NASA's goal of being able to go to about 3 solar radii, then the solar neutrino flux would be 10,000 times that on Earth. We have other ideas about the importance of this concept, such as dark matter searches here on Earth are limited by solar neutrinos, and going away from the sun, you could get 100, 1,000, even 20,000 times smaller solar neutrino fluxes where the Voyager probe currently sits. And then, of course, without waiting for a nearby supernova, the gravitational focus of neutrinos by our sun of the galactic core, which has 10 to the 26 stars, although it's 25,000 light years away, the concentration power of a gravitational lens by our sun would be 10 to the 9, even maybe 10 to the 12. So the work that's being done is as follows. We've constructed these 4 GAG crystals, each being read out by 4 silicon PMs. This work is underway at Wichita State University Physics. We have a veto array that the GAG crystals will be surrounded by, and that's under development at Marshall Space Flight Center. The shielding and mounting around the veto is being worked on by Wichita State University Physics with the help of JPL. And then the CubeSat has been ordered from Nano Avionics for $239,000. We have a dedicated flight electronics that's under construction at Marshall Space Flight Center, high voltage cards, signal card, and logic cards. Payload and flight controls will be done at Wichita State University, as well as with aerospace engineering. And Flight detector simulations being worked on by South Dakota State University as well as Wichita State grad students. Thermal and power is being worked on by Nanoavionics and JPL on our team. And the communications is by electrical engineering here at Wichita State University in cooperation with Nanoavionics and the NASA Near Earth Network. The test detector occupies a third of a 3U CubeSat. The detector unit will be placed at one end of the CubeSat, while the custom electronics card by Marshall Space Flight Center will be adjacent to it. And then the rest of the space is held by normal flight computer, payload controller, avionics, power cards. That is all being part of the Nanoavionics order. Tests of the GAG detector in the lab have been done. Beta decays sources such as strontium-90 and deuterium-90 are similar to the conversion electron spectrum that we would expect. And we're using those to understand how we would tag and visualize and identify conversion electrons. Gamma ray sources are being used to look at the energy resolution, linearity, and signal shape. And this would be similar to the secondary pulse after the excited state germanium decays back into its gallium. And here's the sodium-22. We've also studied cobalt-57 energy resolution, as well as the Ba133 source, which has 4 very close gamma rays, and we can distinguish them. We have these summary plots of the linearity of our GAG detector and the energy resolution. And we're seeing, if you were to project down to about 1 MeV, we're seeing that we should hit somewhere around 5% energy resolution, and that's consistent with the GAG crystals, where people have usually seen those being 4% energy resolution. We've been studying with simulations the double delayed coincidence. The red is the conversion electron being emitted after the solar neutrino interacts on the gallium. And down there in the graph, you can see the spectrum of one event here of what the energy signal would look like in the GAG crystal. Then we would have a delayed pulse. It's a half-life, and it's only 66% of the time this excited state germanium decays back into the gallium, emitting these well-known gamma rays. And our goal here is to look at what they are like. Our test, and then our detector would be sitting inside a Vito ray being built in Marshall Space Flight Center. You can see the detector would sit inside that square. That's the Vito ray. To give you, and there's a cap on it. After the detector gets in there, we would put the scintillating cap on it. And you can see this all relative to the size of a coffee cup. And these tests are underway at Marshall using an americium-241 source from all different directions and sides, and they're getting very good performance of their Vito array. So our hope is would have this CubeSat launched into space. We would then be able to prove space operations. More importantly, because the polar orbit would take it over the pole for 12 minutes where you're not protected by any radiation belt, we would see the gamma rays and cosmic rays you would expect to see as if you were in deep space. And our 8-kilogram detector within a 3U CubeSat would be launched either by a ride share with SpaceX or Rocket Lab. Current costs are $180,000. 2 years of operation, $425,000. And our aim is to launch in the summer of 2024. So thank you very much, and we'll take questions now.